All right, recurrent layers or recurrent neural networks. And these are very important in a hospital setting, especially in a hospital setting. And they process sequential data over time. Now, let me give you a bit more clarification and more simplistic terms for this. So, in healthcare, this is often called time series data. Let's say, for example, daily lab values. We love to get daily labs in the hospital, right? Daily labs, a lot of poking and blood collections, right? Hourly vital signs, medication changes. And this is where you need to understand this concept of recurrent neural networks. And this has powerful implications in any clinical setting. Now, the bottom line is that RNNs work like experienced doctors who remember your medical history, and they can spot patterns over time and even overlook or understand information that is missing. You may have missed, or they may have missed collecting lab work, or somebody forgot to order lab work, or vital signs were not documented. So RNNs can overcome these small issues just like experienced doctors. They don't need all the lab values all the time. They can think and they can prognosticate or hypothesize what actually happened, and they can still come to the right judgment. Now, let's look at this diagram over here. So let's look at this. You're going over time, and let's say this is an EKG. You have vital signs, you have lab values, other labs, and RNNs save memory of previous events, and they coordinate with each other and get you answers. Now, basically, think about how a seasoned clinician looks at a patient's condition over time. You don't just look at today's lab values in isolation, right? The doctor looks at your trends, patterns, any changes over time. The doctor notices when a patient's white blood cell count has been gradually rising over the last few days, or when their blood pressure shows a concerning pattern despite normal individual readings. It might be normal for a textbook patient, but not for you, the particular patient who has his or her own particular needs. All right, so let's go over this. What are recurrent neural networks? Simple definition would be RNNs, they process sequential data. And giving an real world analogy, think about how you evaluate a patient's condition over time. You just don't look at today's lab values. You consider trends, patterns, and changes over time. So we talked about lab values, vital signs, medication changes, disease progression patterns, anything can be picked up. And on the next slide, RNNs maintain memory of previous states while processing new information. Now, I want to actually give you an example of a patient that I looked at 10, 15 years back during my residency. And this patient was coming in an outpatient setting. And I picked up the disease multiple myeloma on lab work over a period of time. And I want to say that previous doctors who had seen this patient before should have picked this up before. I was easily seeing signs of multiple myeloma, including the albumin and protein dissociation and the lab value changes that happen. I'm not going to go into the details about what that is, renal function and other values. All I could see the trend on the patient's lab values in the EMR. Now, these type of mistakes or delays in diagnosis will be prevented by RNNs, and they will be picked up much sooner than maybe a doctor may look to connect all the dots. So to hone in this point, RNNs, they can detect subtle trends that might be missed when looking at isolated measurements, right? So each time the RNN processes a new patient data, it combines current measurements and what it remembers from previous measurements. All right, so now we are going to talk about a real data set, and this may be a lot of knowledge. However, just listen to me and try to focus. And this is just an example for you to get a basic idea about this. And down the line, we will be using these models to try to train and look at our own models. My dear friends, I hope you're loving this. I put a lot of heart and soul into these sessions. These how you can be the human in the loop. in healthcare. This content is free, and for my efforts, I want to request if you can share this with a quick message that you are loving this or that you are learning so much. Share it and send me a message, and I will personally comment below your share to send you a warm note of thanks. I would humbly appreciate you. Thank you so much. All right, so we are here and I'm going to explain everything that you are seeing. All right, so this illustrates an RNN architecture from the MIMIC3 dataset. Now, this is a freely available database comprising of de-identified healthcare data of over 40,000 patients, in a critical care setting. All right, so what are you looking at over here? So you have on the x-axis input variable index. So a variable is like a lab value, a vital sign, a physical examination finding. Now this here gives you 99 different variables collected in the ICU, all types of data. And on the y-axis here, you have the ICD-10 diagnosis codes, and about 20 diagnoses are being represented here. Now, basically, you have the variables, the lab value, the vital sign, the physical exam finding, anything, how it correlates with the diagnoses that are being mentioned. So we are doing Pearson correlations here. Now, Pearson's correlation tells you how connected the two findings are, right? How connected is a vital sign to a particular diagnosis. Let's say sepsis, let's say heart failure, let's say respiratory failure, let's say uncontrolled diabetes, whatever, sugar values, whatever. Now, this color intensity as you're going here indicates strength. How strongly are they correlated? And then in the middle, you have correlation with mortality. These variables, how strongly are they correlated with regards to mortality? You can see in this diagram, lots of information is being provided here. Although this is just for basic understanding of this type of architecture and this type of a diagram for you guys. So this is also helping you predict which variable, which lab finding, which physical exam finding, which sort of diagnosis is much more related to mortality. So lots of information that we can gather from this, and this is highly important for us to have a general idea before we actually go into implementation. Now you can see here, this variable, half of the information is not available, and lots of variables don't have complete information. So RNNs must handle this missing information, and they are able to cope with this missing data and still get you the results that you want. So why does this matter? Of course it matters, right? So RNNs can remember your vital signs and lab values, and it can correlate between different other variables. Or vitals were high when the patient was on this, and this medication. So if for some reason today's blood pressure is missing, it still can predict what today's vital signs would be. So with this, there is sequential learning. So this learns certain patterns happening over time. For example, let's say declining or worsening renal function that follows a rapid heart rate. Let's say, for example, the patient has a high heart rate, and that has been noted to be correlated with a worsening kidney function. So this puts all of these things together into perspective. Now, this helps predict specific outcomes, and different patients, different clinical scenarios, different diseases. This can be very helpful. Now, this sort of demonstrates that RNNs can handle complexity of various types of medical data and also overcomes any gaps or incomplete information from the medical data, from the EMR. Okay, to recap, in real-world healthcare, data is often incomplete. Patients don't get every test every day. Sensors that you may have on, let's say at home perhaps, or in the hospital may be disconnected. Tests are only ordered when clinically indicated, don't need to be ordered every single day. Maybe a documentation may be delayed or incomplete. Lots of times documentation is incomplete. Dear all, I hope you are doing great and that you are liking these lessons and you are enjoying and you are learning. And I did want to suggest something as an option for you. Only if you are one of those who want to have this content in a more organized manner, there is a program that I have set up that you can find in the description. It absolutely is not necessary. However, it is only for those who do thrive in an organized approach, and there just might be a few more goodies there as well. Anyways, I wanted to share this, and now back to the video. In the program, we will also show you how you can be an entrepreneur, how you can go about making your own note writing programs using AI. You don't need technical knowledge. And I'll look to show you how you can do this so you can think about what entrepreneurship ideas you have in mind yourself. Let's go over a specific example. At Johns Hopkins, researchers developed an RNN-based system called TREWS, Targeted Real-Time Early Warning System. And so this continuously monitors patient data to predict sepsis. And we have been talking about sepsis, and sepsis is one of the major killers in the hospital setting if you don't catch it early and you don't provide the right fluids and the antibiotics as soon as possible, right? So RNN architecture for them allows systems to learn that certain sequences of vital sign changes and lab values have predictive importance in sepsis, even when individual values might still be within normal ranges. We know that a heart rate greater than 90 is problematic, and doctors have been trained to memorize sepsis and detect sepsis on lab values. You combine a respiratory rate greater than 80, WBC count greater than 12,000, heart rate greater than 90, temperature greater than 100.4, so on and so on, right? So, but all of these medical guidelines might be changing in the near future because we are getting better and more useful tools, and AI is helping us get there. Now, we will not just look at these values. AI will tell us, hey, in this particular patient, even though the patient is not meeting these values, the patient is going into sepsis, and you better look at this patient very soon. So the RNN architecture allows the system to learn that certain sequences of vital sign changes and lab values, they help predict sepsis, and they happen to predict it before sepsis actually sets in. So sepsis or anything else, you can find trends happening in different types of values, and it will give you an alert much before a doctor or a clinician or the lab will be picking this up. Of course, this is all great, but in real life and in medicine, nothing is perfect, and AI is also not perfect. So RNNs, they can suffer from something called vanishing gradient problem, a vanishing gradient problem. So this is where information from earlier time points gets lost as the network processes longer sequences. It's getting lots of data. Of course, with improvement in our chips, these things should improve. However, this is a current problem. So this is where we have more advanced architectures, and these are called long short-term memory, also LSTM, and something also called gated recurrent units, or GRUs, and these are getting very important. Now, looking at LSTM, and this is of course long short-term memory. And these have been successful in healthcare applications because they can selectively remember important information over long periods while forgetting irrelevant details. Just like an experienced clinician, this LSTMs, these replicate a smart clinician and not taking into consideration all information and homing in on the important information, basically the need to know information. And let's take an example over here. An LSTM monitoring in ICU patient might remember a surgical procedure from days ago, which is important, while forgetting minor vital signs and fluctuations. We don't need to worry about the less important stuff that might even be in normal variation. So for long, short-term memory, you have the patient data, you have forget gate, output gate, input gate, and you have selective memory, that is the important memory. So next we have gated recurrent units. Now, what is the difference between the GRUs, the GRUs, and the LSTMs, right? So LSTMs, the long short-term memory networks, they are generally better for longer and more complex dependencies and variables and data and information. The GRUs, the GRUs, are often a bit simpler. They are a bit faster, and they run on a fewer parameters, not too big. So this makes them more ideal for scenarios where you have limited information and computational resources. Your GPUs are not that great. And the other key difference is that LSTMs, they're more complex architectures with 3 gates. We saw the input, forget, and output gate. We saw the input, output, and the forget gate. Whereas you are looking at the gated recurrent units, the GRUs, and you have the patient data, you have an update gate and a reset gate. And these are one gate and the second gate. So the GRUs, the GRUs, have simplified this into 2 gates, the update gate and the reset gate. And this allows for a quicker training and slightly faster operation. So GRUs, again, are considered them as medical specialists who excel in spotting patterns in time and sequential data. And just as experienced a clinician would notice subtle changes in a patient's condition over multiple visits, the GRUs, the GRUs, track and remember important trends while filtering out irrelevant noise. But they do this in a less complex manner and in a manner where they require less GPU and less processing power. All right, to sum it up, RNN applications in patient monitoring. Recurrent neural networks excel in processing sequential data where order and timing matter, making them ideal for patient monitoring and time series healthcare data, let's say sepsis prediction, medication response, ICU management, monitoring and deterioration, disease progression. So hopefully this was helpful, and we are getting to know all the different terminologies, and this will of course go a long way in all of us being the human in the loop in the future and understanding all these terminologies, and down the line we will be able to practically implement this. Thank you so much. Hopefully this was fun and helpful.